everybody. We are the Solar Airplane Project. My name is Blake Eck. I'm a fourth year dual major with material science and mechanical. This is Lupe, fourth year mechanical engineer, and Fulman, fourth year aerospace engineer. So the background is more of a motivation, and the idea is that for a practical purpose for the drone, imagine that there's a powerful hazardous scenario. In this scenario, while we could send rescue workers in, we could send people to investigate, it'd be much more simpler and more effective way to send a drone out or a UAV to be monitoring the area. Now, by putting this drone in the area, you want to make sure it can fly and sustain flight for as long as possible. So the idea motivating the project is trying to extend the flight time of a UAV by integrating the solar panel system. This allows for students to take a hands-on approach to the aircraft design. We manufacture the entire craft by ourselves. We plan, design the entire craft. We run ANSYS simulations. The entire point of on the project side is so that students can have an opportunity to see a concept and then build it and then watch it progress. It is a research-based project and an experimental-based project. So the goal is to extend the flight time. It's going to have a technical payload. So technical payload in this extent is defined as any electronic systems that are not used for flight. So this includes cameras, sensors, any kind of telemetry data that isn't just for flight navigation. And then the idea is that we have to fly this. While at first we did plan on having autonomous functions, we brought that back because we felt that wasn't quite in the scope of what we wanted to accomplish this year. A secondary objective, or the objectives of this are to, we're trying to understand basically how much power can we provide to this motor versus how many solar panels we can put on it. So we're trying to maximize the surface area, we're trying to maximize the power output, we're also trying to minimize the amount of weight. A secondary objective is more of a personal objective, but this project has been hosted at UCI for approximately 6 years. At first it was in the material science department as how efficient can we make our panels. In the entirety it's been hosted at this school, only one plane has lifted off and it was a kit plane. The entirety of the data sets that people compiled never survived. So in the last 2 years that I've been on this project, the data sets were not saved, they were not carried forward. So secondary objective that we're having is try to provide a basis so that next year, whoever is designing the plane will understand what didn't work for us, what did work for us, and our entire approach. This includes manufacturing documents, design documents, all of our ANSYS, all of our SOLIDWORKS files, CAD files, MATLAB codes. We want to make sure that whatever we do is reproducible and easily found by someone who's never seen this before. So requirements, so we worked off with a maximum of 20 pounds. The initial design was supposed to be a glider design. 20 pounds is really heavy for a plane, but because most of us do not have experience with designing planes, we set it kind of high. The idea too is 24 square feet, so it's a 4x6 area. The idea is that you can put it in a truck bed for ease of transportability. Technical payload of 2 pounds. Minimum flight time has to at least fly 10 minutes. That's by itself. That is purely mechanical. We want the solar panel to extend that flight time by about 15%. So this is going to require extensive testing once it's actually complete. Has to fly at an altitude between 456 to 700. Irvine is at 56 feet above sea level, so has to fly 400 to 700 feet in the air, sustain that for 10 minutes. And it has to have control systems that monitor its environment. So whether that's a camera that's trying to see things, whether it's it could be a sensor that's looking for hazardous pollutants that are in a large area of particulates, or it could be one of the things that we're looking at is a recovery system for when the stall speed, or we go below the stall speed, it can deploy a parachute, it could make sure we dive down to gain more speed. These recovery systems are what we're more banking on. And then the last part is a personal favorite. We have to make an entire thing out of carbon fiber, one component of it. So right now we're planning for the landing gear to be made out of carbon fiber because of its fracture toughness and because it is able to absorb a lot of energy before cracking. The idea though is that by making a carbon fiber component, you're giving students experience with working with composites, which is really big in the aerospace industry, as well as understanding its properties and limitations, how it reacts with humidity, how strong is it with, you hear all these things about it's really strong relative to its weight, but how strong actually is it? Could it land an aircraft? All right. Tony, who will be talking about our timeline.
So here we have the timeline, and this is our progress. So as of right now, we are on progress in week 8 because fall quarter is just the design process. And in this, we will plan to do plane design, we will do analysis in the CAD testing, and we will also do electrical testing as well as choose all of our electrical components. And the goal is by the end of this year, we will be ready for manufacturing. So the process as of right now, we have calculated the optimal airflow for the wings, which is the NACA 6412. We decided this from a mean thickness of 12%, and we tested 4 different airfoils from NACA, and we decided on this one over here. We calculated the tail dimensions, we designed the horizontal and the vertical tail. So here we have a T design for our tail, but we might change that as we see fit because it might not be as feasible as we thought it was. We also ran simulation of each individual plane component so that they would be aerodynamic and we would all be able to put it all together and fly it. We also created standard operating procedures for next year's team to work with. So to come, we have updating our SolidWorks models, doing some more optimization, seeing how we see fit, more simulations on the entire SolidWorks assembly. And then we also got a model airplane kit just to see how it works and then maybe gain more experience so we can build our model. This is our budget so far. In total, we have 1,800, but this is a rough estimate of where our funds would go. So it was estimated that the wing and the tail would take a large portion of our budget. We also have landing gear, avionics, fuselage, and unallocated funding for just extra if we need to add anything or just if anything goes wrong, then we have the extra funds. And I will pass it on to
Thank you. Okay, so our resources, we consider a resource anyone that we can count on to help with Solar Airplane. So our advisor is Professor Yun Wang, and he helps us mostly with administrative tasks. And for Solar Airplane, every unit taken accounts for 4 hours of work. So we have 1 student who's taking the class for 4 units, 3 students taking 2 units, and 14 students taking 1 unit. And we also have 3 volunteers, but they don't have any hourly commitment because they're not taking the class for credit. And we have our weekly meetings on Thursdays from 11 to 12, so that's 1 hour a week. And that's where we review the previous week's tasking, and we also assign tasking for the following week, from Thursday to Thursday. And outside of these regular team meetings, we have 4 sub-teams who also meet on their own. And also the 3 leads, we have 1 meeting a week, and that is a variable amount of time, but it's usually at least 1 hour. And so cumulatively, there's approximately 102 hours put into the project every week from everyone being put together. And this is just our team roster, so it has every member and our advisor, and it just says our positions. And as for the sub-team structure, so Solar Airplane has 3 leads. I'm the mechanical lead, Fung is the electrical lead, and Blake is the project lead. And even though we each have our own distinctive titles, like we do all work with each sub-team because to build a successful airplane, all the components have to be matched together. So for instance, I'm the fuselage team, but I work closely with the tail and the wing teams because I have to ensure that all the components can fit together. And Fung and Blake are in the electrical team, but they still have to work closely with the wing and tail team because those 2 components have electrical components in them, like the ailerons and the rudder that move. So it's up to the electrical team to help them complete that task because they're in charge of electrical. And yeah, so that's it for us. Do y'all have any questions?
Okay, thank you.